staying on top of the global energy transition can, honestly feel pretty overwhelming for you as a listener, right?
Absolutely. It's a lot to track.
Yeah, because there are so many moving parts. But imagine a country deciding to upgrade its renewable energy grid, only to realize that to meet its goals, it has to generate 7 times more power than it currently uses.
Right.
And it would end up consuming almost 80% of its entire natural geography in the process. I
Yeah.
mean, we're looking at a scenario where a single nation attempts to just fundamentally rewire the global economy.
Yeah, and doing it by tapping into the sheer raw power of the ocean.
Exactly. So, welcome to today's deep dive into a really fascinating piece of research. The exact title is Impact of Wave Power Integration and Sustainable E-Fuel, E-Chemical, and E-Materials Exports on Chile's Energy Transition.
And this study is wild because it takes a location that, already possesses some of the absolute best renewable resources on planet Earth and asks this massive, incredibly complex what-if question.
Which usually gets ignored in these kinds of models.
Totally. They use this highly advanced simulation. It's called the LUT Energy System Transition Model. And what makes this simulation so impressive is its resolution.
Right, because it's not just doing basic forecasts.
Exactly. It doesn't just look at broad annual estimates. It actually calculates energy supply, demand, and storage for every single hour of the year, leading all the way up to 2050.
So I was looking at the methodology, and I kind of assumed they just used a basic forecast for something 25 years out. I mean, why is an hourly resolution so critical when we are talking about long-term infrastructure planning?
Well, basically because the power grid has to balance supply and demand every single second. I mean, if your model says you generate enough power over the course of a year, that is completely useless if all that power is generated in the summer.
Oh, right. And then your citizens are freezing in the dark during a windless winter night.
Exactly. So the model uses this 3-level hierarchical framework. It looks at the continental Americas, then zooms into Chile, and then divides Chile into 6 specific spatial nodes.
That is extremely detailed.
Yeah, and by modeling hour by hour, it exposes the brutal physical reality of, when the sun stops shining and the wind stops blowing.
Okay, let's unpack this, because to understand the core premise of this study, we really have to look at the map. We have to look at why the researchers focused on Chile's specific geography.
Yeah, the geography is basically the engine of this entire scenario.
Yeah.
Chile has this massive Pacific coastline stretching for over 4,000 kilometers.
It's huge.
It is. And due to the prevailing ocean currents and the atmospheric pressure systems down in that hemisphere, that coastline boasts a staggering 5,000, 6,000 full load hours of wave energy potential every single year.
Wait, let's break down that metric for the listener real quick, because if there are roughly 8,760 hours in a calendar year, 5,000 to 6,000 full load hours means what, a wave power device is operating at its absolute maximum?
Yes, essentially 100% capacity.
Wow, for the equivalent of nearly 70% in the entire year. That's incredible.
The math totally backs that up. I mean, compare that to a typical solar farm, which, might only hit 20 to 30% of its maximum theoretical capacity over a year.
Right, because of nighttime and clouds and winter?
Exactly. But the resource sitting off the Chilean coast is churning constantly, day and night, summer and winter.
But, and this is the baseline problem the study highlights, despite that massive potential, the baseline cost-optimal models in this study don't actually naturally choose wave power, do they?
No, they don't. When you let this incredibly detailed hourly model hunt for the absolute cheapest possible way to reach 100% renewable energy by 2050, it completely ignores the ocean.
Which is crazy to think about.
Right. It basically opts to cover the Atacama Desert in solar panels and build onshore wind farms simply because those existing technologies are so cheap to mass produce right now.
The market just heavily favors solar and onshore wind.
It really does. So the researchers introduced what they call a wave-favored scenario. They essentially forced the simulation's hand.
Right, they acted like a hypothetical policy counterfactual.
Exactly. They required the model to scale wave power from providing 2% of the country's electricity generation in 2030 all the way up to 10% by 2050.
And they put these down south, right?
Yeah, they specifically placed these installations in the southern regions of Chile, like the South and Magallanes regions, where the waves are just the most aggressive.
Okay, I have to push back on this approach a little bit. I mean, if it is mathematically more expensive, why bother forcing it? It,
Yeah.
it kind of feels like forcing a square peg into a round hole just because we happen to have a lot of square pegs. Wave power is sort of the reliable tortoise to solar's hair.
Hmm.
Why are we paying a premium to drag this heavy flywheel into the mix?
What's fascinating here is what happens to the rest of the grid when you connect that heavy flywheel. The study reveals a really cool mechanical ripple effect.
Okay, what kind of ripple effect?
By forcing the grid to pull 10% of its power from the waves by 2050, the total installed capacity needed for the entire country actually drops by 9%.
Wait, really? You add a new power source, and you suddenly need to build fewer power plants overall.
That's exactly what happens.
Walk me through how that math actually works in the real world. That sounds counterintuitive.
It all comes back to that hourly consistency we discussed earlier. If you only rely on solar, you cannot just build one solar panel to meet your daytime needs.
Right. You have to overbuild.
Massively overbuild. You basically build 3 panels, one to power the grid right now, and 2 extra panels to charge a massive grid-scale battery so you have power tonight and, during tomorrow's rainstorm.
Ah, I see. And wave power fundamentally alters that equation.
Precisely.
Because the waves are always rolling in, you are constantly generating a baseline of power. You just don't need to overbuild thousands of extra solar panels to charge up batteries for a rainy day.
Yeah, the study actually quantifies this displacement. Adding that 10% of wave power displaces an enormous amount of redundant infrastructure.
How much infrastructure are we talking about?
It removes the need to build between 24 and 202 gigawatts of solar capacity and 1.2 to 14 gigawatts of onshore wind capacity.
That is massive.
It is. The wave energy effectively acts as a natural geological battery, dramatically smoothing out the grid and shrinking the system's reliance on expensive chemical electricity storage.
Okay, well, that makes perfect mechanical sense.
Huh.
But the researchers don't shy away from the financial reality, and neither should we. They analyze the socio-environmental data and the economic impact, and the numbers do go up.
They do. In these wave-favored scenarios, the levelized cost of electricity, or LCOE, increases by about 8.2 to 10.4%.
Let's define LCOE just to keep things completely transparent for you listening.
Yeah.
Think of the levelized cost of electricity as the ultimate all-in average price tag of a power plant. You take the cost of designing it, buying the land, building the facility, maintaining the equipment, and running operations over a 25 or 30-year lifespan, and you just divide all of that by every single spark of electricity it will ever produce.
Exactly. So when factoring in every capital and operational cost over decades, the pure electricity gets about 10% more expensive.
Right. And the total system costs, which includes the wider grid, rise by about 3.4 to 4.3%.
Yeah, that's what the model shows.
So for anyone listening right now, you might be asking why any policymaker would volunteer for higher utility bills. I mean, a 4% increase across a nation's entire industrial and domestic energy budget is an astronomical amount of money.
It is, but the justification hinges on a brutal physical constraint that pure economic spreadsheets often, fail to capture, and that is land use.
Ah, right. Because you cannot simply drop a 1,000-foot-tall wind turbine anywhere you please.
Exactly. The study points directly to the Magallanes region in the far south of Chile. It boasts some of the absolute strongest wind speeds on the continent.
But there's a catch.
A big one. The government has officially capped the estimated wind power potential there at 12.7 gigawatts.
Wow. Due to territorial and environmental limits, I assume?
Yes, precisely.
Let's visualize what a 12-gigawatt wind farm actually entails. You were talking about pouring millions of tons of concrete deep into the earth for foundations.
And you need massive spacing between the towers to avoid wind noise effects.
Right, which means carving access roads across thousands of acres of pristine Patagonian ecosystems. I mean, you are permanently altering ancestral lands and disrupting local wildlife corridors.
Yeah, the real-world socio-environmental friction of that kind of onshore development is just immense. But wave power sits offshore, anchored out in the ocean.
So it entirely removes that massive industrial footprint from densely populated urban centers or sensitive terrestrial habitats.
Exactly. And the conclusion they arrive at regarding the domestic impact is highly pragmatic. They basically agree that paying a 4% premium on the total energy system cost might actually be a strategic price to pay for social peace.
Yeah, if paying slightly more for wave power prevents a decade of protests, lawsuits, and halted construction, it kind of transforms from a mathematical inefficiency into a real-world necessity.
That's a great way to put it.
And it's a profound way to look at infrastructure, honestly. We are optimizing for a grid that human beings will actually tolerate having in their backyards.
Right, social acceptance is huge.
So that covers how Chile can effectively power its own domestic economy. But a massive portion of this study pivots to a much more radical idea. What happens when Chile decides to use that exact same infrastructure to power the rest of the world?
This brings us to the export megaproject scenarios detailed in the text. To really grasp the scale of these models, we first need to define the products Chile would be exporting.
Right. What are the actual goods here? The study categorizes them as e-products. Correct.
Yes. And they break down into three specific categories. First, e-fuels, which include e-Fischer-Tropsch liquids, often just called EFTL, and e-kerosene.
And kerosene is crucial for decarbonizing aviation.
Yeah, exactly. Second, you have e-chemicals, such as e-methanol and e-ammonia. And finally, e-materials, specifically e-aluminum and e-steel, produced via hydrogen direct reduction.
So the mechanism behind manufacturing every single one of these e-products basically relies on brute force physics and massive amounts of electricity.
Oh, absolutely. You start with commercial electrolyzers, you pump in water and hit it with a massive electrical current to split the H2O molecules, separating the oxygen from the hydrogen.
And then you have green hydrogen.
Right. And then to make e-fuels, you pull carbon dioxide directly out of the atmosphere and chemically synthesize it with that green hydrogen under immense heat and pressure.
Wow.
Or to make green steel, you bypass traditional coal furnaces entirely and use the pure hydrogen gas to strip the oxygen directly out of the raw iron ore.
And every single step of that chemical synthesis requires a staggering amount of energy. The export targets modeled in this study are incredibly ambitious.
They really are. The researchers modeled a scenario where Chile single-handedly provides between 5 and 30% of the entire fuel and chemical demand for the Americas, Europe, and East Asia.
That is just wild.
And it gets bigger. They also modeled Chile supplying 10% of the Americas' demand and 5% of the total global demand for primary steel and aluminum.
Here's where it gets really interesting, because 5% of global steel demand sounds like, I don't know, a modest fraction until you calculate the joules required to achieve it without fossil fuels.
Yeah, the math is staggering.
It is the equivalent of upgrading your home's electrical panel to handle a new electric car, only to realize you now have to generate enough electricity in your backyard to power your entire city block.
That's a perfect analogy. The study quantifies this 2050 reality. In the baseline scenario where Chile only powers its own domestic economy, its total primary energy demand rests at around 600 terawatt hours.
Okay, 600.
But in the export scenarios, to meet those global quotas, Chile's energy demand skyrockets by a factor of 7. It goes to over 4,000 terawatt hours by 2050.
A sevenfold increase. That is, just to give you a tangible sense of what 4,000 terawatt hours looks like, that is roughly the total annual electricity consumption of the entire United States today.
Right.
We are talking about a single South American country generating the equivalent of the U.S. power grid entirely from renewables, just primarily for export.
And to physically construct that capacity, the study calculates that Chile would need to build between 1,685 and 1,850 gigawatts of power generation.
Wow.
Yeah. This would consume between 71 and 78% of the country's entire exploitable renewable electricity potential.
That is basically pushing their geography to the absolute brink to position themselves as a global supplier.
Exactly.
Which presents a monumental economic opportunity, obviously, but it introduces severe physical ripple effects. I mean, scaling up a national energy sector by 700% uncovers real-world bottlenecks.
Oh, absolutely. Bottlenecks you simply don't see at a smaller scale.
Right. And the most critical vulnerability flagged in this text is the water problem. To make green hydrogen, you need water and electricity. So where does the water come from in a desert?
The study flags this directly. The export scenarios require roughly 1,452 million cubic meters of water by the year 2050.
That's a lot of water.
It is. And since freshwater aquifers in the region are virtually non-existent or just heavily depleted, this massive volume has to be pulled directly from the Pacific Ocean through industrial seawater desalination.
And desalination introduces a whole new layer of environmental friction. You aren't just taking water out of the ocean, you are extracting the fresh water and dumping highly concentrated brine back into the local marine ecosystems.
Exactly. And if we connect this to the bigger picture, the study specifically warns about hydrosocial conflicts arising from this dynamic.
A hydrosocial conflict. meaning the tension between industrial needs and local needs.
Yeah, it's when the allocation of water triggers deep societal fractures. In this scenario, you have local indigenous highland communities, expanding municipalities, and traditional agriculture all competing for a dwindling fresh water supply.
Right, and suddenly a massive international export consortium sets up shop on the coast, prioritizing vast quantities of desalinated water just to manufacture synthetic kerosene for cargo planes halfway across the globe.
Exactly. It creates a situation where a local town might face water restrictions while the industrial plant next door is pumping millions of liters into an electrolyzer.
That sounds like a recipe for disaster. The text notes that inadequate consideration of these local impacts has already begun shifting tensions from the highland communities down to the coastal areas where these new desalination plants are being sited.
Yeah. If local populations feel their basic needs are being sacrificed for global export profits, the resulting social protests could literally paralyze the entire energy transition.
It's a huge risk, but the physical bottlenecks extend well past the water supply, right? There are massive infrastructure hurdles.
Oh, yeah. The study details severe vulnerabilities in the electrical grid itself. Current grid expansion provisions are identified as weak.
And getting the necessary permits for coastal infrastructure is a notoriously lengthy and complex legal process.
Right, and you desperately need those permits for wave power arrays, desalination intakes, and massive export terminals.
Plus, there's an incredible detail in the modeling about internal grid strain. The simulation reveals that to prevent wasting the massive surges of solar power generated in the northern desert, approximately 6% of the total national power generated has to be physically transmitted across regional borders.
Yeah, that transmission hurdle is key.
The study specifically highlights a planned 3-gigawatt high-voltage direct current, or HVDC, transmission line that is absolutely critical just to move stranded solar power from the sunny north down to the population centers in the center of the country.
And that underscores a fundamental role of energy transitions. I mean, you can possess the best solar radiation metrics in the world, but if you lack the heavy copper transmission lines to move those electrons to the electrolyzers, the resource is completely stranded.
Right. However, as the researchers model these bottlenecks, they also uncover some surprising strategic opportunities that could reshape Chile's domestic economy.
Yes, there's a fascinating side note here about e-naphtha.
I found that detail amazing. The study points out that when you are running these massive chemical plants to synthesize E-Fischer-Tropsch liquids for the global market, the chemical reaction naturally produces a heavy byproduct called e-naphtha.
And naphtha is a highly valuable raw chemical feedstock. It's used globally to manufacture plastics and advanced chemicals.
Right.
The study reveals that the sheer volume of e-naphtha produced as a byproduct in these export scenarios would actually massively exceed Chile's expected domestic chemical demand.
Which forces a huge strategic pivot. Instead of just exporting raw energy or basic fuels, acting like a giant battery for the global north, Chile could use that excess naphtha to seed an entirely new, high-value domestic chemical manufacturing sector.
Exactly. They could shift from being a simple resource exporter to an advanced industrial powerhouse.
But of course, transforming into an industrial powerhouse creates a massive logistical headache.
Oh, the shipping fleets.
Yes. You are generating 4,000 terawatt-hours of energy to create e-ammonia and e-methanol, but those chemicals hold zero value if they're trapped in South American storage tanks.
Right. The bottleneck shifts entirely from production to global shipping. The supply chain logistics at this scale dictate geopolitical power. I mean, if you rely entirely on foreign shipping conglomerates to move your national product, you capture a fraction of the economic value and remain highly vulnerable to global shipping rate fluctuations.
So what does this study suggest?
The researchers suggest that to control this massive supply chain, Chile might need to seriously evaluate developing its own national shipping fleet.
And the text mentions leveraging existing historical and corporate ties, right? They specifically point to the German shipping giant Hapag-Lloyd, which previously absorbed the historic Chilean shipping company CSAV.
Yeah. By developing a national fleet or a massive strategic joint venture, Chile could lock down control over the entire value chain.
That is wild to think about. They would control the solar panel in the Atacama, the wave converter in the Pacific, the electrolyzer on the coast, and the cargo ship docking in a European port.
It represents a staggering level of vertical integration on a national scale.
So what does this all mean? When we pull back and look at the entirety of this modeling, a very clear picture emerges. The global energy transition is not simply about swapping out a coal plant for a wind turbine.
No, not at all.
We are talking about engineering entirely new global economies and supply chains from the atomic level up. We're talking about continental-scale land use decisions, where the placement of a wind farm requires balancing ancestral rights against global carbon quotas.
And crucially, as this research demonstrates, we are talking about fundamentally redefining our relationship with the oceans.
Exactly. Leveraging them not just as a source of immense, consistent wave energy, but as the raw material for the fuels that will power the next century.
Implementing a transition of this magnitude demands a level of holistic, system-level thinking that, frequently just gets lost in the mainstream discourse.
It really does.
The sheer physical scale of the infrastructure, the intricate chemical synthesis, and the vital importance of securing social acceptance make this an unprecedented human undertaking.
It is precisely why rigorous, hourly modeling like this is so vital to our understanding of the future. We owe a huge thank you to the authors of today's source material, Impact of Wave Power Integration and Sustainable E-Fuel, E-Chemical, and E-Materials Exports on Chile's Energy Transition. The depth of this study has given us an incredible amount to unpack.
It really has. And building on the data we have explored today, there is a final, critical geopolitical dynamic to consider.
What's that?
Well, if a nation like Chile commits nearly 80% of its entire exploitable renewable capacity, triggering an infrastructure scale-up 7 times its current size, solely to feed the world's hunger for e-products, they are taking an immense calculated risk.
Because what happens if global demand shifts unexpectedly?
Exactly. What happens if a disruptive new energy technology emerges a decade from now? Could an entire nation's meticulously built trillion-dollar infrastructure become the world's largest stranded asset?
That is a terrifying thought.
Or, on the flip side, are we currently witnessing the birth of renewable superstates that will eventually wield the exact same geopolitical dominance and leverage that fossil fuel empires command today?
That is a staggering question about the future of global power. We invite you to ponder exactly who will hold the leverage in a post-fossil fuel world. Until next time, keep diving deep.